Greetings, welcome to another edition. In this session, we'll be looking at an introduction to Laplace Transform. So as a point of departure, what we are going to be looking at would be the introduction to Laplace Transform, finding the Laplace Transform of typical functions, which you must try and know on top of your head, and also looking at the applications where we will need our knowledge of Laplace Transform. So let us quickly start by defining exactly what is Laplace transform. So by definition, Laplace transform is a linear operator that transforms a function that transforms a function. So that transforms a function f of t to f of s. The operation does exactly that. And there's a couple of things which we need to be aware of, which is that the sign for our Laplace transform is usually something like that. So once we see the sign, it means that we are taking the Laplace transform of whatever which is inside the brackets. So it means if we have this sign and then we have f of t there, all what that means is we are taking the Laplace transform of f of t. Okay. So there's a couple of things which we need to be aware of, which is that when you take the Laplace transform of f of t, what you get is the integral, and this is where the mathematical definition comes of Laplace transform. It is the same as taking the integral from 0 to infinity of that function f of t multiplied by another function, which is e to the power of negative st dt. This is the mathematical definition of Laplace transform. And also the Laplace transform can be written as previously mentioned, the Laplace transform of f of t can be just written as f of s. And there's two things which we need to be aware of here. The t which is there represents or is the time domain, or that function, it is the time domain representation of f of t. But if you look carefully at the right hand side, you will observe that something interesting is happening. So you'll see that what you see is you see an s there. So that s there is the frequency domain. It is a variable which is in the frequency domain. So that is what s is. It is a variable which is in the frequency domain. So which means f of s actually is a frequency domain representation of our original function. So make sure that you have a feel of what is going on. You are aware of the sign, and also you are aware of the mathematical definition of Laplace transform. So where do we use it is the question which we should ask next. Where do we use Laplace transform? And the answer to that question is very easy, and it's a couple of them. So we use Laplace transform in the following instances. So we use it when we are trying to solve differential equations. And remember where differential equations come from. Usually this course is done in signals and systems and processing, but differential equations, all what they represent is they represent a system. So that is what you should always remember at all times, that differential equations which I'll just call DE, they represent a system. So differential equations represent systems. So someone would have done some modeling and then they ended up having a differential equation, and then they solve for whatever input or output. Another application which we usually use Laplace transform in is to perform convolution. So it is to perform convolution of two functions, because in the frequency domain, convolution, as you will see, will just be taking the Laplace transform of the respective functions and then making a product out of them. Then you find the inverse, that would be the convolution of the two functions. Let's look at the third equation. So the third equation, in part it follows, or the third application, it links to the first one, where we are going to use this to solve boundary value problems, which is just, it falls under differential equations. And I'm going to task you to go and find the others. So I need you to go and find other applications where we use Laplace transform. Now let's go to the next page and write down our definition and then have a look at problems. So if you remember, we previously mentioned that if you're taking the Laplace transform, which is indicated by the sign of f of t, it is the same as having the integral from 0 to positive infinity f of t e to the negative st. So a couple of things which you need to note here is that these limits will remain the same unless the function has other limits which are overwriting these ones. So if you look at these limits here, we need to make a note that they will remain the same unless the function has limits which are overwriting this. So the limits of integration will remain the same unless, if you think carefully, unless the domain of the function which we are taking the Laplace transform of is different. So unless the domain of the function, and the function in this case, it would be the one which we're working with, f of t, unless its domain is different. Then if the domain is different, the limits will change. So whatever the domain of the function is will supersede what we have here. So please make sure that you understand that the limits of integration will remain the same unless the domain of the function f of t is different. Okay. So with that said, another important aspect which we need to look at is the s. This s is always equal to alpha plus j w. Others would just prefer to call this beta. It doesn't make much of a difference. So beta or w. And what is very important as we'll be doing our integration is that the real part of s, which will always be alpha, we've done complex numbers, is assumed to be always greater than 0. This is an assumption which we always make. And the reason behind making this assumption, you will see, it is because when we substitute the upper limit as infinity, you do not want your Laplace transform to blow off to infinity. So that is why we make assumptions around the real part of s, which in this case will be alpha. Okay, so let's go and have a look at a couple of functions which we need to take the Laplace transform of. So I'll start off by looking at this one. So we'll call it example 1. There we go. We are expected to determine the Laplace transform of f of t, where f of t is given as 1. So let's go ahead and do that. So if you look carefully, I'll find the Laplace transform of f of t. And remember that by definition, we'll be integrating from 0 to infinity, unless you are given a domain that will succeed this one. So we always have f of t multiplied by e to the negative t dt. So for our case, as you can see, our f of t is 1. So it means that I'm just finding the Laplace transform of 1. What is it going to be? It's going to be the integral from 0 to infinity. The function is 1 multiplied by e to the negative st dt. If you look carefully, how we can easily integrate this. When you integrate, we get e to the negative st divided by, remember that we are integrating with respect to t. So we should divide by whatever which will multiply the exponent, which in this case, it will be negative s plus c, and then we put in our limits of integration, which is infinity and 0. So if you look carefully, for the first part, what we have is the limit, and there's something I want to remind you before I even go there. And what I want you to remember is something which you should have done when you were doing some early mathematics, which is that the limit as x approaches infinity of, let's say, e to the negative alpha x, this will approach 0 as long as the alpha is greater than 0. So meaning whenever you put in the x here, which is infinity, as long as everything on the exponent is going to end up being negative, that will approach 0. So if I evaluate my limit or my integration limits here, you will see that what we will have is we'll end up having the limit as s, not s but t, remember, as t approaches infinity, that is the first part of e negative st divided by st. Then we deal with the lower part. We have e negative s. Remember, the lower limit is 0 divided by negative s, like that. So if you look at the top part, after the note which I wrote above there, you should remember that we said s will be greater than 0. So remember that the real part of s, we said it will be greater than 0. So all what this means is that this portion here will approach 0. And if you look carefully, our answer, the negative and the negative, will end up cancelling to give us a positive. And e to the power of 0, by now you should know that it will be 1. So all what we have as our answer is simply 1 over s. So in summary, the Laplace transform of 1 is equal to 1 over s. That is what we get. So let's go to the next example. We will call it example number 2. So welcome once again. Let's have a look at example number 2, where we are required to determine the Laplace transform of f of t equals e to the power of alpha t. So let's go ahead. What we know is that by definition, Laplace transform of f of t will always be equal to the integral from 0 to infinity of f of t multiplied by e to the power of negative st dt. So let's go ahead and start doing our Laplace transform. So we're taking the Laplace transform of e to the alpha t, and this is the same as the integral from 0 to infinity of e to the alpha t multiplied by e to the negative st dt. With this, there's something which you learned from you know, when you were very young, about multiplying the same bases. So what happens to the exponents? We add them. So this integral is the same as finding the integral from 0 to infinity. And the base will now be the same. And we add the exponents. So if you look carefully, I will have alpha minus s, and then I'm going to have the t like that. And the t will be sitting there. And then we will have dt there. Okay, so now I can go ahead and do my integration. But in case you got confused, let me maybe write it as alpha t minus st like that. Then only below, I can just separate them or combine them and just have e to the power of alpha minus s multiplied by t dt. So what is very important to remember is that you are integrating with respect to t. So when we integrate with respect to t, this means that what we are going to have is e to the power of alpha minus s times t divided by alpha minus s. Because remember, by chain rule, we always divide by whatever which is multiplying there. That is by chain rule. So just a quick recap on that. I can just write it for you here and say, remember. And what I want you to remember is that the integral of e to the power of, let's use px dx, it's going to be e to the power of px plus c divided by p, because p is what multiplies the x and we are integrating with respect to x. So essentially that's what we used here. Then we just need to put in plus c, then put in the limits infinity and 0. Okay, so now let's go ahead and do our substitution. So usually the infinity, we avoid putting it as a value there. So I'm going to say the limit as t approaches infinity of e to the power of alpha minus t minus s times t divided by alpha minus s. Then for the lower limit, I'm going to have minus, this will be e to the power of alpha minus s. Remember, t is now 0, divided by alpha minus s, like that. So what you should remember, at least when you get to exponentials like this, the infinity term, we always want it to approach 0. So an assumption that is taken here is that the real part of s is bigger than alpha. So an assumption here, because we want our system to not blow off to infinity, because if it does, there's just no utility in whatever we are doing. So here the assumption is that the real part of s will be bigger than the alpha, which means the overall exponent here, as far as this is concerned, it will be negative when you look at the real part. And what does that do? What that does is when we put in infinity, all of that just becomes 0. That's the utility. And then this portion here will just amount to 1. So if you look carefully, our answer will simply be negative 1 over alpha minus s, which you can just push the negative and end up having 1 over s minus alpha. So what does this mean in conclusion? What this means in summary is that the Laplace transform of e to the alpha t is simply 1 divided by s minus alpha. That is what it means. This is example number 2. Let us now go to example number 3. Now let's have a look at example 3, where we are required to find the Laplace transform of f of t, which is equal to sine of alpha t. So as you know, the Laplace transform of f of t is always given by our integral from 0 to infinity of f of t multiplied by e negative s dt. So which means when we're looking at the Laplace transform of sine of alpha t, what this will be equal to, it will be the integral from 0 to infinity of sine of alpha t multiplied by e to the negative st dt. This is our integral which has been set up, and we now need to think very carefully in order for us to work this interval or this integral properly. So one would opt to use a couple of rules like your integral by parts, but I'm not going to do that. So what I need you to remember is this here. So what I need you to remember is from Euler's form. I will call it Euler's identities, because this is where this comes from. From Euler's identities, what I need you to remember is that sine theta is equal to 1 over 2 I, which is for complex numbers, multiplied by ei theta minus ei negative I theta. This is what I want you to remember. But also what I want you to remember, which is useful, is that your sine theta can also be written as the imaginary part of ei theta, like this. So we have two forms. So what I'm going to do is, we have already worked with an exponent, so it's easier for us when we separate this into exponents before we put it there than for us to go and do some hectic integration by parts. So if you look carefully, sine of alpha t is just the same as 1 over 2i into e I alpha t minus e I alpha t, like this. So I can go ahead and plug this. So if I go to the equation where I'm taking the Laplace of f of t, what you will see is that we'll have an integral from 0 to infinity of our sine, which is that, and then multiplied by our e negative s t dt, like that. Okay. And if you look carefully, we can now just pull out the constant, which is 1 over 2i. And when I pull out the constant, what you will see is that we'll have a 0, infinity, so I'll have ei alpha t multiplied by e negative st, then minus e negative I alpha t multiplied by e negative st dt, like that. So now all what I need to do is to go and integrate this. So let's go ahead and do some integration of those portions which are inside. So the first thing which I can do is to just combine them so that it becomes a bit easier, you know, to work around with them. Okay, there you go. And then now we can start doing our integration. So we'll have 1 over 2i, open the brackets. If you look carefully, we'll have ei, or e in brackets. Let's see what we are going to have. So we'll have e into I alpha minus s times t, and then this will be divided by, if you look carefully, I alpha minus s. And then that is the first portion. So let's go to the second portion. If you look at the second portion, it has a negative there. So we'll put in the e negative I alpha minus s multiplied by t, and this is divided by, if you look carefully, negative I alpha minus s, and this will add the c, then put in the infinity. So now let's go ahead and deal with this. So I'll have 1 over 2I outside. Then inside I'm going to have the limit as t approaches infinity, that is for the upper limit. So I'll copy all that portion and deal with it. So remember that we never want our answer to be approaching infinity. So what we do is we assume that the real part of s is greater than 0. So it's positive. So this negative here makes it to be a negative exponential. Then when you put in infinity, all of that just goes to 0. So I just need you to think of the behavior of the graph e to the negative x. If you remember how it behaves, it behaves as follows. So it goes down as the x approaches infinity, the graph approaches 0. So this top portion here will be approaching 0, and that top portion there will also be approaching 0. Then we have the bottom portion, which will be minus minus to give us a plus there, and it will be e to the minus. So it will be e to the power of, when we put in the lower one, the lower limit, it will be negative. Let's come here. So the first term will be negative. So that was I alpha minus s. It will now be multiplied by 0 divided by I alpha minus s, like that. Then the other part will be minus minus, which will be plus. So we'll have e into the negative I alpha minus s, and the t is 0. And this is divided by negative I alpha minus s. So if you look carefully, the top terms will just easily become 1, and even that term will become 1. So this means that what we have is equal to 1 over 2i into, if you look carefully, it will be, when I just quickly pull out the negatives, so it will be negative 1 over alpha, or I alpha minus s, and then the other one will be plus 1 over negative I alpha minus s. So there's a couple of ways we can rewrite this so that it looks a bit more intact. So let's quickly attempt to do that. So that will be 1 over 2i. So what I'm going to do is I'm going to pull the negative down so that I have 1 over s minus I alpha. Okay. Then on the other term, I'm going to pull the negative up, which is what is going to cause this negative here. Then I have s. If you look carefully, it will be plus I alpha. Then we do the common denominator here. So 1 over 2i. If you look carefully, we'll have s minus I alpha multiplied by s plus I alpha. And we're doing a common denominator, so this will be s plus I alpha minus s minus I alpha, like that. Close the brackets. So let's see if we can make up some space here and conclude this problem on this page. So this is one of the problems which you must make sure that you at least have a sense of how it's done. Sine and cos, when the exponential term. So let's see when we simplify this what we get. So if you look carefully, this s here will end up cancelling with that one. And what we will end up having is 1 over 2i. If you look carefully, s plus I alpha minus s plus I alpha. That is what we have there. Then divided by, what I want to remind you is the multiplication of conjugates. So complex conjugates. So what I need you to remember is that if you are multiplying complex conjugates, like, in fact, this is as good as even a difference of two squares, if we can use that. So let's maybe call this a difference of two squares kind of problem, if you look carefully. So if I quickly do it on the side, you'll see that we have s plus I alpha multiplied by s minus I alpha. So when you multiply the s's, you'll get s squared plus, and then you'll get, in fact, minus I alpha s plus I alpha s. And then you'll have plus, when you multiply I alpha x with minus I alpha x, what we I alpha multiplied by minus I alpha, we get alpha squared. So essentially that denominator there becomes s squared plus alpha squared, which is what we are supposed to put here, s squared plus alpha squared. And if you look carefully, there's terms which are going to cancel nicely. And this 2i here, if you look carefully, these will add up and it will end up cancelling like that. So essentially, if you look at our problem, our answer, let me maybe try and make one more line there so that I'm confident that you are not confused in any way. So if you look at this term and that term, this one and that one, they are going to add up and give you 2i alpha. So the 2i from the bottom will cancel with this 2i, which is there. You see? So all what we are left with is that the Laplace transform, therefore, of sine of alpha t will always be given by alpha divided by s squared plus alpha squared. So make sure that you are able to do this derivation. And this is example number 3. Okay, so let's now have a look at example number 4, where we are required to determine the Laplace transform of f of t, which is equal to cos of alpha t. So this is not too different from the problem which we did previously, where we were dealing with our sine. So let's quickly write down our definition. So it is the same as integrating from 0 to infinity f of t multiplied by s or es t and then dt. So what I want you to remember with cos is what we learned somewhere back in first, second, in high school for others, is that cos of theta is the same as 1 over 2 into ei theta plus e negative I theta. Very important identity which is going to save us here. So this means that our cos of alpha t is just the same as 1 over 2 open bracket ei alpha t plus e negative I alpha t. So this will take the similar approach with the one which we took for sine. So let's go ahead and start finding our Laplace transform for cos of alpha t. So this will be an integral from 0 to infinity. Take our cos, put it there, dt, and this will be the same as taking the integral from 0 to infinity. Let's write our cos in a way which is easy to work with. If you look carefully, there's our cos, and it's going to be multiplied by e to the power of negative st dt. Okay. So now I'm going to look at the far right. If you look carefully, we can factor out a half. And then we have exponential terms that can add up. So we have e to the I alpha t, which will multiply when we distribute with e negative st, and then plus e negative I alpha t multiplied by e negative st dt, like this. So let's go ahead and collect these according to the bases. So if you look carefully, we'll end up having e to the power of I alpha t minus st, then plus e to the power of negative I alpha t. So I'm not supposed to put the t inside here. Okay. So alpha minus s, and then the t is common when we add the numerator and the denominator. So remember, when you have am times an, it's am plus n, like that. Okay. And then do not forget the dt. So let's quickly do our integration here. So we have 1 over 2 into, we are going to have e to the I alpha minus s times t. This will be divided by I alpha minus s, then plus e to the negative I alpha minus s divided by negative I alpha minus s plus c, and then we put in our integration limits 0 to infinity. Okay, so we can now go ahead and quickly evaluate what is going on. So the upper integral is infinity, so I'll put in t as t approaches infinity. Then I'm going to take this term and put it here. So because our t is approaching infinity, and remember we said s will be a positive number, the real part of s, so that whole thing will approach 1, will approach 0, and that will also approach 0. I've explained that before why it is. Then for the other portion, which is minus, if you look carefully, we put zeros there, so you'll have e to the I alpha minus s multiplied by 0 divided by I alpha minus s, then plus the other one, negative I alpha minus s, we multiply by 0 divided by negative I alpha minus s, like this, and then we close the brackets. Okay, so let's go ahead now and quickly simplify this and see what we obtain. We're looking for the Laplace transform of cos alpha t. So the numerators, you know that e to the power of 0 will always give you 1. Even that portion will give us a 1. So it means that the answer which we have is 1 over 2 into, if you look carefully, 1 divided by I alpha minus s plus 1. So remember, there will be negative because of that negative. So I'll take that negative outside here, equal, I'll put it here. And then this will be divided by negative I alpha, then minus s, like this. So we can easily rearrange this, such that we have the s on the other side. So this will be negative half. So if I push the s up on the negative on the denominator, I'll have negative 1 divided by s minus I alpha. We do the same even with this one. We have a negative 1, and then this becomes s plus I alpha. Then as you can see, we have a common denominator there. So what we are going to have is negative 1 over 2 into, just look at this carefully and think about it. You will have a negative 1 multiplying s plus I alpha if we make a common denominator, then minus 1 multiplied by s minus I alpha, like that. And the denominator will simply be s minus I alpha multiplied by s plus I alpha, like this. So if we look at what happens here is on the numerator, you will end up having negative s, negative I alpha, negative s plus I alpha. And then on the denominator, if you look carefully, you will end up having s squared plus alpha squared when you do the foiling there. And if you look carefully, there's terms that cancel out nicely, like this one and this one. So all what we have left is equal to negative a half into the minus s, and minus s give us minus 2s divided by s squared plus alpha squared. And if you look carefully, we have a minus 2, so the minus and the minus will make a positive, and then these two will cancel. This 2 and that 2 will cancel, so that we get an answer which is going to be s divided by s squared plus alpha squared. So what is going on? In summary, whenever you are taking the Laplace of cos of alpha t, the answer is simply s divided by s squared plus alpha squared. That is how you get to the final answer. So welcome once again. Let's have a look at example number 5. So for example number 5, we are going to be looking at the Laplace transform of f of t equals t. And by now your definition, you should be comfortable with it. We've written it many times. It should be the next thing in your mind. So we're given that our function is f of t, so which means we are looking for the Laplace transform of t. So what is it going to be? It is going to be the integral from 0 to infinity, t multiplied by e negative st dt. And when I look at this here, what is going on here and here, I remember something. That for this problem, unfortunately, we need integration by parts. And in general, if you remember, integration by parts is as follows. So if we are integrating a product of two functions, u and dv, the answer will always be equal to u minus v, or u times v, minus v du. This is what integration by parts is. So we need to we need to quickly choose here which one is going to be u and which one is going to be dv. So my u is going to be t. So what you usually do is you usually choose the polynomial to be the one which is going to be u. And the reason why you choose the polynomial to be u is because when you derive, it will eventually get to 0. And once we've chosen our polynomial, whatever which was multiplying t becomes dv by default. So which means our dv is e to the negative st. So as you can see, our formula will need u, but it will also need du. So if I quickly find du, you will see that it is 1. But if I find v, which is just the integral of dv, which in this case it's the integral of e to the negative st dt, that will simply be e to the negative st divided by negative s. Okay, so let's go ahead now and plug this to our formula. So it means that when we are integrating t, e to the negative st, 0 to infinity, and then dt, don't forget, our answer will be u times v. So our u, if you look above, it is t. Our v is e negative st divided by negative s. And this is evaluated between 0 and infinity. Then minus the integral of our v. If you look at our v, it is what we found here, which is e negative st divided by st. And our v should be multiplied by du. But our du is 1. Then dt, and this is between 0 and infinity. So let's evaluate that part. So all what I have is I have negative t e to the negative st divided by s 0 to infinity. And when we look at the part which is inside there, when we integrate it, if you look carefully, you will see that what we will get will be e to the negative st divided by negative s all squared by chain rule. And then we are going to have plus c, then I can put in my limits this way. Okay, so my answer I can just write in one form, which is going to be negative t e to the negative s divided by s, and then minus, if you look carefully, e negative st divided by s squared plus c. I can just now put in the limits here because they are common. Now let's go to the next page and see what this amounts to. Okay, so let's put in our limits now. So for the upper limit, we have a limit as t approaches infinity of that first part. I quickly need to fix the t of this first part. So if you look carefully, this becomes an easy problem, really, because this portion as t approaches infinity approaches 0. And then this one here would approach infinity. But when you multiply 0 and infinity, you will get 0. And then that portion there will also approach 0. Okay. Then we go to the lower limit where we put in 0. So wherever there's t, we put in 0. So minus s times 0 divided by s. We'll put in that minus. Then minus e to the negative s 0 divided by s squared. So if you look carefully, this term here will end up being 0, the entire term, because of that 0 which is at the front. But if you look carefully, we have a negative here and a negative there. So this leaves us with an answer which is good looking. But most importantly, before we go to the answer, remember this portion here will be 1, e to the power of 0. So this means that our answer is simply 1 over s squared. So this means that therefore, whenever we're looking for the Laplace transform of t, our answer, which you will find, will always be 1 over s squared. You can do this for t squared, t cubed, t to the 4, the 5, the 6, and so on. And there's something I want to give you as a general formula. So I'll say here, generally, as you do this, what you will realize is that the Laplace transform of t to the power of n will be n factorial divided by s of n plus 1. This is what happens. In our case, we had n is 1. In our case, we had n is 1 because that was the power of n. So if you look carefully, when we take the Laplace transform of t to the 1, the answer becomes 1 factorial, which is 1, then divided by s of 1 plus 1, which, as you can see, it gave us 1 over s squared. So this formula works. And that concludes example number 5. Now let's have a look at example 6. In example 6, we are required to determine the Laplace transform of f of t, where f of t is cosh, which is just hyperbolic cosine. And the approach is the same as what we would do for all other functions, except that there's something very important which we need to remember as part of doing our work, especially with the hyperbolic functions. So what I need you to remember, which will make our life to be easy, is this identity here. So I need you to remember that hyperbolic cosine of theta is the same as 1 over 2 e theta plus e minus theta. This is what will save us. We are good as done once we get this done. And here we are going to use, the way which we are going to be so smart is shocking. So you remember that previously I did the Laplace transform of e to the alpha t with you. And what we found was that you will have e, or you'll have 1 minus, or 1 over s minus alpha. So essentially, what is here, you will subtract there. So look at how smart we are going to attempt to be. So when we're taking the Laplace transform of cos of alpha t, this will be equal to the integral 0 to infinity. We have half of e to the power of, remember, it's cos, so we'll have alpha t plus e negative alpha t, then multiplied by e negative st dt. Okay, that is what we have. Maybe let me quickly write down this here, which is that our cos of alpha t will simply be a half into e alpha t plus e negative alpha t. Okay, so with this now I can pull out in the half. When I pull out the half, if you look carefully at what I have, is I have e alpha t multiplied by e negative st plus e negative alpha t multiplied by e negative st. So I can really attempt to be smart here by quickly using what we know, which I wrote in blue, which if you look carefully, if I have a half and I'm taking the integral from 0 to infinity of e alpha t multiplied by e negative st dt, I can separate even the other integral, and you'll see what I'm going to do. 0 to infinity e negative alpha t multiplied by e negative st dt. So if you look at what is going on here, it is as good as saying I'm looking for half the Laplace transform of e alpha t plus half, if you look at the integration, the Laplace transform of e negative alpha t. And I can use what I've derived already on the next page to easily find the Laplace transform for cos or hyperbolic cosine. So let's go ahead and do so. And this is the benefit of making sure that you derive your identities, then you know them on top of your head, because whatever which multiplies t there is what we are going to subtract here. So which means for this problem, we'll have 1 over 2 multiplied by 1 over s minus alpha. The other one, I'll have 1 over 2 multiplied by 1 over s minus. If you look at what is multiplying t here, it is minus alpha. So that is why we are going to have minus alpha like that. And if you look carefully, we'll end up having a half times, maybe let me go down. We'll end up having a half times 1 over s minus alpha plus a half multiplied by 1 over s plus alpha. So I can factor out the 1 over 2 if you look carefully. Then I have 1 minus alpha plus 1 over 1 plus alpha. And this is just the 2, which I can just make a common denominator, s minus alpha, s plus alpha. Then if you look at the top, we'll have s plus alpha plus s minus alpha. And if you look carefully, there's terms that are going to cancel out. And what we are going to have is a half multiplied by, at the top, 2s divided by s squared minus alpha squared. And as you can see, there's going to be nice cancellation of terms there, leaving us with s divided by s squared minus alpha squared. So essentially, therefore, the Laplace transform of hyperbolic cosine of alpha t is equal to s divided by s squared minus alpha squared. That is what we have. And if you look at how this compares to cos, so let's quickly have a look at how it compares to cos. So cos, we did it previously, and let's see. The answer we found was more the same, but the difference was at the bottom. So the Laplace transform of cos of alpha t was nearly the same as squared alpha squared, but the difference was on the sign here. That is what caused the difference. So you can imagine, you can go ahead and do for sine, which we will quickly have a look at. So let's jump to example number 7. Okay, so here's example number 7. We are required to determine the Laplace transform. And what is very important, which I need you to remember here, as we did with hyperbolic cosine, is that hyperbolic sine of theta is the same as 1 over 2. So very important, there's no i's for hyperbolic sine and cos. It will be e theta minus e negative theta, like that. So we can use exactly what we already know. So we know that whenever you're taking the Laplace transform of a function, f of t, this is the same as taking the integral from 0 to infinity, f of t, multiplied by e negative st dt. So with that said, I can now go ahead and deal with this problem, because my sine of alpha t, or hyperbolic sine, is simply 1 over 2, and then e to the alpha t minus e to the negative alpha t, like this. So let's go ahead and plug this in. So this means that if I'm looking for the Laplace transform of that hyperbolic sine, all what I'll be doing is I'll be integrating 0 to infinity of this here. Let's just copy it. And it will be multiplied by e to the negative st, then dt. So if you look carefully, I'll pull out the half, and I'm integrating from 0 to negative infinity, and what I have is e alpha t multiplied by e negative st. That makes me happy. And then I'll have a minus 0 to infinity, and if you look carefully, I have e negative alpha t times e to the negative st. So if you look at these carefully, this here is as good as the Laplace transform of e to the alpha t, and the other portion, which is this portion, this is as good as the Laplace transform of e to the power of negative alpha t. But what I'm going to do, I'm going to use the advantage that I already know, this, we've done it before. Remember what we know. What we know is that the Laplace transform of e to the alpha t becomes 1 over s minus alpha. So pay attention to something. Whatever which comes here, we are going to subtract there. So if you look carefully, then it means that I will have half of Laplace transform e to the alpha t minus half of the Laplace transform of e negative alpha t. So this will end up being half of 1 over s minus alpha minus 1 over 2 multiplied by 1 over s minus, what is multiplying the t there is minus alpha. Okay, so let's take that to the next page and go and conclude this problem. Just have a look. Okay, so if you look carefully, I can factor out the 1 over 2 because it is common, and I'm left with 1 over s minus alpha minus 1 over s plus alpha. And if you look carefully, we can make a common denominator here. And when we make a common denominator, we multiply by the respective terms on the numerator, s minus alpha, then divided by the common denominator, s plus alpha, s minus alpha, like that. And if you look carefully, we'll have 1 over 2, we'll end up having s plus alpha minus s plus alpha divided by, at the bottom, that is a difference of 2 squares, at least when you reverse it. So which means when you multiply, you'll get s squared minus alpha squared. And if you look carefully, there's terms which are cancelling, that and that. And what we end up having is 1 over 2 multiplied by 2 alpha divided by s squared minus alpha squared. And if you look carefully, we can easily cancel the 2's. So when we cancel the 2, what you should be able to see is that when we take the Laplace transform of hyperbolic sine of alpha t, the answer which we are getting is alpha divided by s squared minus alpha squared. And the question we should ask is, how does this compare with sine of alpha t? And as you remember, the way which this will be different, if you remember the Laplace transform of sine of alpha t, we found that previously. And what we found it to be was alpha divided by s squared and then alpha squared. So what makes the difference is the sign. So here we have a plus and there we have a minus. That is what makes them to be different. So make sure that you are able to do these calculations. Let us go to example number 8. Okay, so for our example 8, we have an interesting looking problem where we have e to the alpha t multiplying g of t, and we are expected to do the Laplace transform. What I want you to understand out of this example is what we call a frequency shift. That is what will happen here. And a frequency shift, where it arises, it is caused by exponential terms. It is caused by exponential terms in the time domain. So in this case, that exponential term would be e to the power of alpha t. It is going to cause a frequency shift. So how do we work around this? So if you think carefully, if I'm taking the Laplace transform of f of t, it means all what I'm doing is I'm taking the integral from 0 to infinity of e alpha t and then g of t multiplied by e negative st dt, like this. And there's a couple of ways which we can easily, work this problem out. But one way which we are going to approach or take the approach of is that we'll collect the exponentials. So this will be 0 to infinity, and I'll have g of t. And when I collect the exponential terms, you'll see that we'll have alpha minus s multiplied by t dt. Okay, that is what we have. And if you think of what has happened here, we can easily change the domain further for example, what we can do is we can say let W be equal to, so remember that what we are doing here is we are trying to find the what you call it, the Laplace transform. So we can let W, let's pull out. So one thing I need you to see is that the first, before we even go there, let's maybe write it in a form which will easily look like what we already had. So if I have G of t, and then I have e to the power of negative, so remember we had negative st, so I'm going to have negative of s minus alpha. When I factor out the negative, things become this way, then dt, like this. So what I'm going to do is I'm going to let the W to be equal to s minus alpha. And now I want to write the entire expression in terms of W. That is what we want to do. And if you think carefully, because we want to write everything in terms of W here, W is essentially a dummy variable. So if you think carefully, when we just put in our integration 0 to infinity, this becomes just G of t, then e to the negative W times t dW. This now is sitting exactly in the position which S was sitting at. And if you think carefully, this would typically be, because we have G, it means our function is going to be G of W. But what is W? You should remember that W is that. So this means that the Laplace transform of e to the alpha t, G of t, will always be given by G of s minus alpha. So all what you do is in the frequency domain, you do a shift. That is why I made a comment at the beginning that we have a frequency shift. That is all what you do. So it means in whatever function that you have, which is multiplied by e to the alpha t, you will find its Laplace transform wherever you see fs, you put in s minus alpha. Let us consider an example so that we make sure that we understand what I'm saying. Okay, so let's have a look at example number 9 so that we see if we can apply what I showed you previously. So what I showed you was that if you take the Laplace transform of alpha t multiplied by, let's say, any function f of t, the answer will simply be the Fourier series of f, but wherever we would put s, we'll put in s minus alpha, which is the frequency shift. And I said the exponential terms, they contribute a frequency shift. So this means that if I'm looking for the Fourier transform of f of t as an example, what I need to do is I need to recognize that this term here is going to cause a frequency shift. So what I can do is I can just find the Fourier transform of cos of alpha t, which is already what we know. But to account for the exponential term which causes a shift, wherever I see s, I'm going to put s minus alpha. So for the cos one, if you remember, we have s over s squared plus alpha squared. That is what we get. But because of the shift, I'm going to replace s with s minus alpha. This one here, it comes from the exponential term. Okay, so let's go ahead and see what we obtain. So it means that whenever we're taking the Laplace transform of e alpha t, let me even use different letters, because once it's alphas, it just becomes confusing. So let's use beta there, and we'll use beta. So we'll use beta for the e. Okay, where else? Minus beta here. So if we have e to the alpha beta t, which is just the number, multiplied by cos of alpha t, the answer will simply be, wherever there would be s, because of this exponential term, we'll have s minus beta. And this will be divided by, wherever there's s, we have s minus beta all squared plus alpha squared. That is how we would obtain the Fourier transform, not Fourier transform, but Fourier series, sorry, the Laplace transform for example number 9. So let's go and have a look at example number 10, then 11, then we conclude the session. Okay, so let's now have a look at example number 10, where we're required to find the Laplace transform of e to the beta t multiplied by sine to the power of alpha t. What is most important, which you need to remember, is what I taught you, which is that the Laplace transform of e to the beta t multiplying any function is just the same as that function, and all what you do is wherever you see s, you put in s minus beta. So you find the Laplace transform of the actual function. Wherever you see s, you'll replace it with s minus beta. So what that means is that when we're looking at the Laplace transform of e to the beta t multiplied by sine of alpha t, all what I need to do is find the Laplace transform of sine of alpha t. Then after finding it, wherever I'm going to see s, I'm going to replace it with s minus beta. That is all what we do. So the Laplace transform of sine of alpha t we already have. We found it previously. Where is it? Here it is. Okay, let's go and put it up. So that will be alpha divided by s squared plus alpha squared. Wherever we see s, we're going to replace it with s minus beta. So as you can see, the Laplace transform finally of beta t multiplied by sine of alpha t will be equal to alpha divided by, wherever we see s, we put s minus beta plus alpha squared, like this. Then let's have a look at example 11 and we conclude the session. Okay, so let's have a look at example 11. Very important is what we have discovered, that if you're taking the Laplace transform of e to the beta t multiplied by a function f of t, the answer is the same as you finding f of s, which is the Laplace transform of f of t, and wherever you see s, you replace it with s minus beta. So what does this mean then for us? It means that if I'm taking the Laplace transform of e to the beta t multiplied by t to the power of n, I need to go and find the Laplace transform of t to the power of n. Then wherever I'm going to see s, I'm going to replace it with s minus b. Lucky enough, I did touch on the Laplace transform of t to the n some other time earlier in this session, which is that it will be n factorial divided by s n plus 1. So this means that our Laplace transform of e to the beta t and then t to the n will simply be n factorial divided by s of n plus 1. Then wherever we see s, we are going to put s minus beta. So the final answer for this question t to the n, it will simply be n factorial divided by, wherever we see s, we put in s minus b. So I have s minus beta, and the power is n plus 1. So this will all be raised to the power of n plus 1. There are many other Laplace transform forms which you need to make sure that you know, but this was to just give you an introduction and a feel of the general table which you will see of Laplace transform and how you eventually get to those. So I hope that this session was helpful and it will be even useful in the future. So please make sure you like, subscribe, and for now, take care and bye-bye.